right. So I think we might as well go ahead and get started. It looks like we've got a number of people online, so thank you everybody for joining us today for Chris Shepard's 2-year review. We're going to try to hopefully make this as seamless as possible. The faculty should have received his CV and narrative statements and research or teaching portfolios in the email. As is normal, we're going to share the screen with Chris and let him give us a seminar. We'll have time for questions at the end of that. We're just going to ask for everybody to stay muted except for the speakers. So I'll mute myself here as soon as I'm done introducing Chris and turn it over to Chris. If you have questions at the end, I know there's a fancy option in Zoom for holding your hand up, but I'm going to suggest people just do this, and then I'll be kind of monitoring the screen and letting him know what questions are there if he's having a hard time, but I think Chris feels like he'll be able to do this. If you don't have volume, feel free to just hit the chat button and put your questions in via chat, and we'll try to get to those. When we get through his question period, Abby will take back over the screen. We'll remove and make sure the people who need to be removed from the space have been removed. And then we'll turn it over to Chris Matoka for a presentation of his materials and a faculty discussion at that point in time. Have I missed anything, Chris?
I don't think so.
I don't think I have either. We're also going to be videotaping it, and so I'll send out an email when this is all concluded. If you want to watch the video, we'll have you contact Abby, or this one we're going to put on YouTube, I think, aren't we? So it should be up on our station, and so it should be normal there. Okay, so to briefly introduce Chris. Chris joined us in 2018. This is his 2-year review, and we're right on time. He started, I think, July 1, so a fiscal year appointment. He came to us directly from completing his PhD at the University of Arizona in the Soil, Water, and Environmental Science department. He got a Master's of Science also from that same group in the University of Arizona, and he did his BS in Environmental Science at the University of Virginia in Charlottesville. Chris, go ahead and take it away.
Okay. All right, good afternoon, everybody. I just want to say thanks to Rebecca for the introduction, and then thank you all for joining us today over Zoom. I've actually really been looking forward to giving this talk because I'm really excited to talk with you all about some of the progress that we've been making in the pedology group over the last 2 years. I just wanted to start with an overview of my activities for the last 2 years. I was hired in July of 2018, as Rebecca said, and I was hired with a 65% research, 25% teaching, and 10% service appointment. So that is a slightly higher service appointment than what's typical in the department, but I'm going to talk about that specifically in a few slides. So on average, I've getting pretty close plan to maintain my distribution effort averages at least around that range. In the last 2 years, I've published 2 peer-reviewed manuscripts. Both of those manuscripts were for my dissertation work, and the journals that they were published in, the average impact factor was 3.28. For the field of soil science, the journals in the soil science field, the median impact factor is 1.997. So I'm actually getting my research into slightly higher tier journals, so we're having a slightly higher impact. So I'm actually really excited about that. I currently have 1 manuscript in review at Soil Biology and Biochemistry. That's also for my work that I did at the University of Arizona. And then I have 4 manuscripts right now currently in different states of draft. So 3 of those manuscripts are also from my dissertation work at the University of Arizona. And 1 is from work that I have initiated here at Kentucky. So I'm really excited that we're finally starting to get some work together that we could move forward to submitting to a journal. I've been actively applying for and searching for funding opportunities. So in my time here, I've applied for 4 nationally competitive grants, and I do have one currently pending. It's an NSF Critical Zone Collaborative Network grant. That is that sort of large pending grant that you do see. So I'm actively searching and currently in the process of simultaneously drafting a few different proposals, which I'm actually going to talk about today. I received one state contract upon arrival at Kentucky, and I'm going to talk specifically about what that is because it is tied to my service component. I've also been pretty active in applying for opportunities internally to UK. So applying for what's available in the department, what's also available through CAFE, and then also some opportunities that have come through through the university. I also initiated the process and submitted my Hatch proposal last year. And I think at the end of last year, either in November or December, my Hatch proposal was finally approved by NEFA and made active. So I'm excited to have that finally done and finally on the books. So I did say this just a few minutes ago, but I was hired at a 25% teaching effort, and so far I've averaged about 26% for the first 2 years. Obviously, most of that teaching is almost all of that teaching is from this 1 year. So in fall of 2019, I offered soil judging and soil morphology and classification. So those classes were offered for the first time last fall in a few years. So I was actually pretty excited that I was able to get enough students to fully offer those classes last semester. And I want to talk more specifically about soil judging in a few slides. We did do pretty well at soil judging, and I was able also to offer the advanced soil judging course, PLS 406, this spring. So that was really exciting that we were able to prepare for the national competition this spring because we did so well last fall. And then also this spring, I offered a new course, a special topics PLS 697 course called Applied Environmental Statistics. And this class has been pretty heavily subscribed by the graduate student population. So I wanted to take a little bit of time to talk specifically about what this class is. So as I said, I developed this new 3-credit statistics course that specifically focused towards graduate students in the environmental and agronomic sciences. So I tried to build this course around the application of statistical techniques using the R statistical package. I've seen a lot of job announcements recently that have said that some experience with R is either a preferred or a necessary job requirement. So I think providing our students this experience is very beneficial. And I think you can see how interested some of the students in our programs are about this course, just because I did have 23 students registered for the first time this class was offered in this certain form. And I've also had a lot of students from different programs. So predominantly students came from the IPSS program, but I also had a number of students from entomology, from the earth and environmental sciences, plant pathology, forestry, as well as biology. So I was really excited that I had this interdisciplinary group for the first time teaching this class. It made it a lot more fun. So in fall of 2019, I put together my first soil judging team ever. I actually had never interacted with soil judging or ever been a soil judger. So for me, this was like a totally new experience, but it was really exciting and I had a ton of fun doing it. So last fall, we led 4 undergraduate students to the Southeastern Regional Soil Judging Contest that was held in October of 2019 at Virginia Tech. So we were able to take these 4 undergraduate students out to Virginia to sample and describe soils in a completely different landscape than what we have here in the bluegrass. So I think it was actually a really great experience for them to be up in the mountains and to see some really different soils. We actually did really, really well at that competition, and I was so happy and pleased with how well we did. We ended up doing well enough to qualify to go to the national contest, which would have been held actually next week at The Ohio State University. Unfortunately, that was canceled due to current events. But we're really excited to get back next semester and to go compete again at the University of Tennessee at Knoxville in the Southeastern contest next fall. I do have a slightly higher service component or service appointment than what is typical in the department. And the major component of that is providing a soil morphology course for the Kentucky Cabinet for Health and Family Services. This course is the first course that public health employees need in order to become certified to evaluate sites for on-site waste management systems. And this course is that state contract that I received upon arrival at Kentucky. So I offer 3 4-day long courses per fiscal year, and those classes are held here in Lexington. Additionally, another part of my service component is being a go-between between the university's land grant mission and the NRCS activities around the National Cooperative Soil Survey in the state. And part of that, I actually have a pending cooperative agreement with the NRCS in Kentucky to provide technical support for soil survey activities here in Kentucky. Also, over the last 2 years, I've tried to stay active within SSSA and the Tri-Societies, and I was elected chair of the SSSA Soil Mineralogy Division. So I will serve as chair in 2021, which I think is when we are in Salt Lake City. So I'm actually really looking forward to that. I think it will be a lot of fun. So that was a summary of what I've been doing for the last 2 years, but I'm really excited to talk about some of the science that myself and also others in my lab group have been doing. So we approach pedology from a critical zone perspective. So for those of you who are not familiar, the critical zone is this concept within earth sciences that is this thin outermost veneer of the Earth's crust that goes from the top of the tree canopy down to a depth of fresh bedrock. So in pedology, we're really uniquely situated in that we understand, or we work to understand, how soils are integrated into this critical zone, this life-sustaining zone at the surface of our planet, and how soils are interacting with each component of the critical zone, whether that be biology, whether that be the atmosphere, or whether that be, say, the parent material that makes up that soil. So understanding these fundamental processes from this perspective of CZ science helps us to develop better management practices. It also helps us to better trace contaminations when they are present within the environment. And they can help us develop better strategies for sustaining ecosystem services. So in my lab group, we're really interested in trying to understand how soils are evolving and how they're responding to changes in climate, biology, topography, parent material, and time. All of these different state factors that Yinny formulated in the early 1940s go into creating the critical zone and what we think of as soil evolution. So in doing this work here at Kentucky, I wanted to identify several different pathways of soil evolution or pedogenesis that were important unsolved issues or important research questions here in Kentucky. So in talking with colleagues and in doing my own reading, I've really settled down into these 3 different components or 3 different pathways of pedogenesis. The first one I'll talk about today are fragipans and fragipan formation. The second one will be about the relationship between karst processes and soil formation. And the third one will be understanding how phosphorus influences soil carbon dynamics, especially here in the bluegrass. So first we're going to talk about fragipans and fragipan formation. So we're working to understand in my lab group how we can better quantify the rates and mechanisms of fragipangenesis, particularly in the less mantled landscapes that we do see here in Kentucky. For those of you who may or may not be familiar, fragipans are dense, brittle, naturally occurring soil layers that have these large prisms surrounded by these whitish gray cracks in between. So if you look to the image to the right, this is a quintessential fragipan from Crittenden County out in Western Kentucky. So this is the fragipan horizon down here, this dense, brittle layer. We see these large reddish brown prisms surrounded by these whitish gray cracks. Due to their properties, fragipans have a pretty heavy impact on the uses that we use for these soils. So fragipans can limit root growth because they're so brittle and dense. They are not very penetrable to roots. They can also limit the water holding capacity of these soils. So the volume that contains available water for plants is pretty limited with soils with fragipans. Also, due to their high density, they can alter soil hydrologic functioning. When water does infiltrate down into the soil, it often will hit the pan, the top of the pan, and will have to move laterally because it cannot infiltrate any deeper into this dense layer. For these reasons, fragipans have a pretty heavy impact on agricultural production in Kentucky. They can also have a large impact on construction as well. Actually, you cannot place an on-site waste management system on a fragipan. You either have to remediate that soil or put in a rather expensive alternative system. Additionally, nutrient management in areas with fragipans is also largely affected by their presence in large parts of Kentucky and the eastern US. Fragipans are really common soil horizons. They actually occur across 1/3 of Kentucky. And even though they're so common, we don't really understand a lot about their formation, how long it has taken to create a fragipan or their rates of development. And we also don't really understand how certain soil physical or chemical properties how they generate particular fragic properties or characteristics, like the brittleness and the strength that we do observe in these soils. One of the major reasons why I think that we have a hard time necessarily understanding fragipan formation is just because of the sheer number of different theories that have been proposed about fragipan formation. So many of you are likely familiar with some of the work that Dr. Karathanakis did in the late 80s and 90s, where he focused on cementation of fragipans by amorphous aluminosilicates and iron oxides. But there are other theories too that have substantial support, like clay bridging, so the bridging of larger particles with clay minerals, or this idea of hydroconsolidation, where you have these repeated wet-dry cycles, which cause a collapse of the larger soil particles within the fragipan. So within my group, we thought about what maybe are the remaining questions that surround fragipan formation and fragipan horizons. And really, because we do have all these different theories that are available, we wanted to answer what are the dominant processes that generate fragipans, particularly in less mantled landscapes like what we have here in Kentucky. We also wanted to better quantify what the rates of fragipan formation are, particularly in Western Kentucky. And that's actually something that has never been done yet. No one has actually dated fragipans to determine how long it takes to create one. And finally, we wanted to better understand how the evolution of particular soil physical and chemical properties eventually generate the common fragic characteristics or properties that we see, like brittleness and like strength. In order to do this, we went to Western Kentucky and we worked with several scientists with the Soil Survey out at the Owensboro office. And we identified 8 different pedons that we sampled in 7 different Kentucky counties. So we went to sites in Breckinridge County, Grayson, McLean, Crittenden, Caldwell, Trigg, and Christian counties. And we sampled profiles at each of these locations. So here you can see these 7 or 8 profiles that we did sample, and some of them look very similar. So we see Crittenden, Breckinridge County, Christian, they have these characteristic prisms with these characteristic whitish streaks. But we do see a lot of variation between these different soils. So what are the processes that are generating all of these different morphologies that we do see? So we went out, we sampled, and we brought these soils back now, and we're beginning to analyze them. And we're still in the preliminary phases of doing this, but Hannah Somerville, my graduate student who is working on the project, has done a lot of great work to better quantify what we do have already. Fragipans, one of their main characteristics is that they do have this very high bulk density. And one of the surprising trends that we did find was that this fragipan bulk density related strongly and linearly with fragipan sand content. It actually had an R squared of 0.91. So what we think is happening here is we're seeing evidence for this hydroconsolidation theory, that with these larger particles and these wet-dry cycles, we're packing them closer and closer together to generate higher and higher bulk densities within these soils. So more sand, you can more closely pack these particles together, and you have higher bulk densities within these horizons. One of the consequences of the hydroconsolidation theory is that our prism material would have to have densified first, and then later the material then filled in the voids that existed between those prisms to form what we see now are the cracks. So we went out when we were sampling these fragipan soils, and we did a kind of a tedious sampling where we sampled the bulk soil horizon material. And then we sampled material from the prism specifically, which is this sort of brownish, reddish area in the soil. And then we sampled material specifically from the crack. So that's what is this whitish gray material here. So after doing this, we can bring this material back to the lab, and we can geochemically isolate these materials to see whether or not they're derived from the same parent material sources. So that's what you see in this figure here on the left. The bulk soil material, so material sample from the entire horizon, is in red. The crack material is represented in green, and the prism material is represented in blue. And so down here, I just have an immobile element, titanium, on our x-axis, and then I have the depth profile here on the y. So we do see that there is somewhat of a differentiation, at least in two fragipan horizons within this sampled soil, between our crack and our prism material. So that may indicate that there is some differentiation between these materials, and it may provide some support for that hydroconsolidation theory for this particular fragipan soil in Western Kentucky. Similarly, with some of the data that we were able to get from some of the geochemistry work that we've done, we can also calculate what are known as tau values. So tau values are simply molar ratios between an immobile element and a mobile element that are indexed to the concentrations of those elements within the parent material, or what we think of as the original soil material. So in this case, we're using titanium as that immobile element, and we're just looking at aluminum and iron here. So when we're looking at the distribution of this tau value with aluminum, or with this tau value for aluminum with depth, we do see that there is greater loss of aluminum from our prism material and from the bulk soil material. And excuse me, just to orient yourselves, the negative values here mean that we've lost more of this element, and positive values would indicate that we've actually gained some of this element. So we do see that in general, we've lost most of the aluminum, or we've lost a significant amount of aluminum from our prism material, but we've lost very little aluminum from this crack material, which makes sense. When we do see significant amounts of aluminum within our soils, we do see that we have a whitish color typically associated with them. So that is what we do see in this crack material. When we begin to look at the loss or gain of iron with our tau values, we now see that we actually have less loss of iron from our prism material, and we have greater loss of iron from our crack material. Again, this makes sense. As we are stripping out this iron, we should be losing that reddish color that we do still see maintained in our prism material. But what I'd also like to point out to you is that we also do see this kind of reddish brown, rust-colored stain right at the boundary between our crack and our prism material. So this may indicate that not only is there a less loss of iron, but there are potential cementations of iron oxides within this fragipan prism within the soil. So it may point to evidence for hydroconsolidation, which is then followed by cementation with these iron and these aluminum oxides, and potentially also some of the amorphous aluminosilicate cementation that Dr. Karathanasis speculated about in the 80s and 90s. Moving forward, we're working to quantify more fragipan properties, and we're also working to quantify the ages of these fragipan soils. So we'll be doing this for the first time for fragipan, so we're really excited about some of this work. And we're going to be using two different techniques, optically stimulated luminescence and cosmogenic radionuclide dating. We've been working with Drs. Lewis Owen and Paula Figueredo at NC State University to do this work. And this work has been written into a almost ready to submit NSF proposal that's going to go in, I'm hoping, in the next few weeks to geobiology and low temperature geochemistry. And I will say also that Dr. Chris Matoka has been helping a lot on this as well with a lot of the mineralogy work that we've been doing. The next pathway of petagenesis that I identified and am really interested in better understanding is the relationships between karst processes and soil formation here in Kentucky. So moving a little bit closer to the bluegrass. The bluegrass is a specific geologic region that is underlain by a phosphorus-rich limestone unit that's called the Lexington Limestone Stratigraphic Unit. Limestones weather and dissolve relatively quickly within the humid environment of the Earth's surface. And when we do have a significant amount of dissolution of carbonated rocks, we do end up generating a special type of landscape, a very unique landscape that we call karst. So you likely are all probably pretty familiar with karst, just living here in Lexington. But the topography that are created in these karst landscapes can be highly variable. So we can see that we have these sinkholes that form, these disappearing streams, and we also get this very heterogeneous drainage system that is generated within our karst, within our limestone rocks. So if you think Mammoth Cave, how extensive and how heterogeneous that cave is, you can imagine how heterogeneous some of the drainage networks maybe are in these areas. A lot of work has been done in trying to understand some of that hydrologic variability. But I think less work has been emphasized on understanding how variability in soils in these landscapes might relate to some of those karst hydrologic processes. So for many of us, when we do think about karst and say sinkholes, we do think of these kind of catastrophic cover collapse sinkholes. This is a very famous one that opened up under the National Corvette Museum in Bowling Green, Kentucky in February of 2014. Fortunately, the reality is that most sinkholes and karst features are actually pretty gentle features. This is actually one of the sinkholes that we were working at out in central Kentucky in Versailles. So we were working to develop a better understanding of some of the variability that maybe exists within karst systems, and we specifically targeted sinkholes because they do show up at the surface of our karst systems. So there are often a lot of soil mantled sinkholes that we see locally here in Kentucky and then also throughout the world. So we were interested in developing better linkages between some of that karst hydrology that we do see and also our soil properties. So we established two different catinas and two different sinkholes at the C. Orrin Little Research Center farm. So today I'm going to be talking about the cow sinkhole, some results we have from what we call the cow sinkhole, and then some also results that we have from what we're referring to as the horse sinkhole. So these are just images here of Rebecca Ramsey and myself out sampling in these two different profiles in these sinkholes. So as I said, we established two catinas or topo sequences in these two different sinkholes. So here on the right, you can see the topographic profile for our horse sinkhole. So the catina here is just an organization of our hill slopes and our soils into particular landscape positions. And this can help us better understand how topography maybe influences some of the soil properties that we see in these different areas. So to do this, we went out and we sampled 5 different landscape positions in our horse sinkhole. So we sampled the toe slope, the foot slope, side slope, shoulder, and summit. And we did the similar thing in our cow sinkhole. So this is a topographic profile for that cow sinkhole, and we have sample soils from our toe slope, foot slope, side slope, and summit. The cow sinkhole was a slightly smaller sinkhole, so we were unfortunately not able to sample the shoulder position in this area. These are images of each of the different soil profiles that we sampled in both the horse and cow sinkhole. So what you can see from these images is that the soils in our toe and our foot slopes are much browner compared to the soils that we do see higher up on our catinas or our topo sequences at the side slope, shoulder, and summit positions. Additionally, we can also see that the horse sinkhole, the soils on average do appear to be redder in color compared to the soils that we do see in our cow sinkhole. So already we're seeing some field morphology indicating that there are some differences or some variability that exists between the soils within these two different sinkholes. Once we brought these soils back to the lab and we started doing analyses of these soils, we did end up finding that there were significant differences between these two different sinkholes. So first on the left, we have elevation on the x-axis, and then we have redness rating on the y. So the redness rating just gives us an indication of how brown or red the soils are. So a lower value would be browner, and a higher value would be redder. And so sometimes we can use this redness rating as an index of the amount of weathering that a soil has received. So we do see that in general, our cow sinkhole soils were more brown in color compared to our horse sinkhole soils. So that does support what we were seeing in the field. When we look at pH, on average, we do see that the pHs in our horse sinkhole are more acidic compared to our cow sinkhole. So the horse sinkhole is in red and the cow sinkhole is in white. So we do have pH on the x-axis and then depth on the y. So there's just potentially greater stripping of some of the base cations from the soils in our horse sinkhole. So that may indicate that, again, there is some different degree of weathering, or maybe there's more water fluxing through that horse sinkhole compared to our cow sinkhole. That's also supported when we look at the base saturation percentages for the summit and toe slope positions in both our cow and horse sinkhole. So again, the cow sinkhole is in the white and the horse sinkhole is in the red. And we do see lower base saturation percentages for our horse sinkhole compared to that cow sinkhole. So it does seem to be more stripping, more loss of our base cations from the horse sinkhole. Annie McGraw has been working she's a master's student in my lab, and she's working really hard to analyze all these different soil properties that we have. And so some of the things that we also have found is that the carbon and nitrogen contents have varied quite significantly. They vary quite significantly between these two different sinkholes. So first, just looking at carbon, we do see that there's greater amounts of carbon, or total carbon, in the soils in our cow sinkhole compared to our horse sinkhole. We see a very similar pattern for our total nitrogen content of the soils of our cow sinkhole relative to our horse sinkhole as well. So that makes sense. These usually correlate to one another. When we look at the distribution of our carbon to nitrogen values with depth for our two different sinkholes, we do see that there are extreme differences. So in our cow sinkhole, again here in the white, our C to N ratios are pretty constant throughout the entire soil profile for the most part. Now, when we look at the C to N ratios with depth for our horse sinkhole, we see a very different story. We see that on average, they're similar to our horse or our cow sinkhole at the surface, but then they decrease substantially with depth. So clearly there is less carbon, there's greater amounts of nitrogen to carbon. And so there could be a few different things that are driving this particular trend. What we were thinking was that there's either potentially a management difference between these two different areas on this farm, or this could also be a legacy of some land use history that has also been taking place. There are also potential differences due to landscape feature age, and that's supported by some of the differences in the soil properties that we did see, redder colors in the horse sinkhole versus the cow sinkhole, and also greater stripping of the base cations. This also could be due to some sort of difference in hydrologic activity. Potentially, there's greater amounts of water that are infiltrating through this horse sinkhole into the karst features below. So there's some greater loss of carbon relative to nitrogen for some reason from these soils, or there's potentially greater nitrogen-rich runoff coming from the surrounding agricultural fields that are entering into this horse sinkhole as well. So we're continuing to explore some of these different relationships for these different soils in this system. So while we've only sampled 2 different sinkholes, when we do start thinking about the number of karst features that are present throughout Kentucky, there are numerous sinkhole features throughout just Woodford County and also Kentucky alone. So if we think that just the amount of variability that we are seeing within our own soils maybe exists, if we think the variability that between these 2 different sinkholes is similar to what we see across all of the different karst features within just Woodford County, there's likely a substantial potential for differences in carbon storage through these different features. Also, all of this variability within the soils within these karst features may also be playing a crucial role in modulating some of the karst hydraulic responses that we are seeing in these different landscapes. So this work is currently being prepared for a manuscript that's being led by Annie McGraw, again, the master's student who's working on this project in my lab. And also this work led to my inclusion in a pending NSF proposal to the Critical Zone Collaborative Network that is in with the NSF currently. The final pathway that I was interested in exploring in the past few years is better understanding how phosphorus maybe influences some of the carbon dynamics, the soil carbon dynamics that we see, particularly here in the bluegrass. The phosphorus cycle is pretty unique compared particularly to carbon and nitrogen in that it does have no gaseous component. The vast majority of phosphorus that is available for plants and microorganisms in the soil is derived from rock weathering, particularly from the weathering of apatite group minerals. There is some phosphorus that is deposited on our soils through atmospheric deposition of dust, but that can be minimal in most areas. And of course, humans are applying significant amounts of phosphorus to our soils through fertilizer applications. While phosphorus is an essential macronutrient, it is considered less influential in modulating the carbon cycle, particularly compared to nitrogen. And mainly the reason why is that less phosphorus is typically needed by organisms compared to nitrogen. And also phosphorus is utilized at different ratios to carbon by different types of organisms as well. But we are sitting here in the bluegrass on this high phosphorus area. So the question, we're uniquely situated to ask some pretty interesting questions about what phosphorus maybe does do in a phosphorus enriched environment on the carbon cycle. So if we do have significant amounts of primary phosphorus available for plants and also for microorganisms, do we see greater amounts of phosphorus and potentially carbon being contributed to the organic phosphorus pools? And then do we also see greater amounts of phosphorus with carbon absorbing onto mineral surfaces and becoming components of different iron and aluminum phosphorus oxides? So does the presence of greater sources of primary phosphorus lead to potentially greater soil carbon storage in these environments that have this enrichment of phosphorus naturally? So to do this, we've been working to quantify the distributions of soil carbon and phosphorus with depth. So within my lab group, this is some of the work that Dr. Pamela Obura has been working on. And she's really been focusing on characterizing the soil physical, chemical, and mineralogical properties for 2 auger cores that we sampled from a hilltop, from a summit position out at the North Farm. So the soil that we sampled was in the Monterey Bluegrass Soil Series complex. So we auger to two separate depths, 266 centimeters and 232 centimeters, where we hit bedrock. So that Mari bluegrass soil is forming on the Lexington limestone formation or unit that we talked about previously. And so this unit is enriched in these phosphorus-bearing minerals like apatite. And there's two particular members that are of interest that do bear these phosphorus minerals. They're called the Greer and the Tanglewood members. And so they are the members that we do see the Mari and the bluegrass soils forming on. We're still working to quantify and characterize a lot of the soil chemical, physical, and mineralogical properties that we do see from our sampled auger, from our auger cores, but we do have some preliminary results to share. So here we have depth on our y-axis, and we have total carbon on the x-axis. And so the two auger cores that we sampled are in red and green on this figure. We were also able to sample at that same hilltop the Mari soil pit that is open permanently in that location. So that is represented in this blue color. And then we also have some archived soil material that was sampled from the early 90s that we also included within this analysis. So we do see obviously an exponential decrease in the total carbon for these different auger pits and auger cores and pits. So that's nothing very exciting or interesting. But we do see these bumps in carbon at 100 centimeters, at about 150, and we see similar things in the other auger core as well. So we do see that there is some interesting, there are some small increases of soil carbon at depth when we do look at these different soils. So where is that soil being stored? What is it possibly being associated with? So we were thinking that it might be locked up in organometal complexes. So on the x-axis here, we have the aluminum concentrations that were extracted from sodium pyrophosphate selective extractions. So that sodium pyrophosphate extraction breaks out organometal complexes specifically. And so they can give us, aluminum particularly can give us an index for the presence of these complexes within our soil. So we do see at the same depth where we do see these increases, these small increases in carbon, we do see increases in the potential presence of these organometal complexes, particularly between 100 and 175 centimeters. So that's pretty exciting because there's been some recent work by Spoon in 2020 where we do see that greater phosphorus content may support the formation of aluminum, particularly aluminum and iron oxide organometal complexes. So these complexes can have a significant amount of surface area, so they may allow for greater carbon sequestration. And the reason why this is of interest is because we do see that for organic phosphorus in managed systems that is associated with the clay size fraction, that there is more resistance of this organic phosphorus fraction to change, to loss under these management conditions. So that may mean that carbon that is locked up with this organic phosphorus in these organometal complexes may be more stable over long periods of time. So as I said, this work is sort of in a preliminary phase, and we're still working to quantify a lot of properties. We've already done a lot, but we still have a lot more to do. So going forward, we're hoping to quantify the concentrations of carbon and phosphorus associated with the crystalline and amorphous, as well as the organometal complexes, those mineral fractions within the soil. We also want to fractionate the phosphorus to determine the associations between particular mineral and organic soil components as well. And we're hoping to expand our sampling both to other limestone units that are poor in phosphorus, like the St. Louis and St. Genevieve limestone units out in Western Kentucky, as well as other lithologies here in the state. And we're also hoping to expand to include both managed and non-managed ecosystems. And I am currently working on a draft of this proposal that will eventually go to the Division of Environmental Biology to support this work. I also wanted to talk about a few additional projects that I've been included on while I've been here at Kentucky. So the first one, I've been working with doctors Matt Crawford and Jason Dortch to examine some of the landslide dynamics that maybe relate to landscape evolution in Eastern Kentucky. We're also currently working on a NSF proposal draft as well for that work. And then also working with Dr. Brad Lee, we've been analyzing 30 years of soil test data that have been generated by the UK Regulatory Services. So here we see two figures, one for soil test phosphorus and another for soil test potassium. The red are soils that were been sampled and tested from agricultural fields. And the white comes from urban homeowners. This may be from gardens or particularly from lawns as well. So we do see over time that our soil test phosphorus from 1990 to 2019 is decreasing, which is good. That's what we want to see. We want to see our growers in the state applying less phosphorus because we don't really need to apply any more than a certain amount in order to get the benefits. We do see the opposite though, the opposite trend for our homeowners and our urban areas. We do see still increases in phosphorus over time. So we still need to be reaching out to these areas and say, hey, you probably don't need to be applying more phosphorus. When looking at potassium, we were actually pretty surprised to see this downward trend with soil test potassium in our agricultural soils. So we don't necessarily think about potassium being a nutrient we always have to apply, but we do see that we are on a downward trend, and we are getting kind of close to where we might actually begin to recommend to growers to apply phosphorus. We really see no change in our urban and homeowners soil samples, but that's not very surprising. They wouldn't necessarily be thinking about, oh, I probably need to apply potassium, particularly to my lawn. So one of the other things that we were able to do with this data set is that we were able to look across the state in each county what the average soil test values were for both phosphorus and potassium. And we took averages over 3 years from 1990 to 2019. So this first movie is just a change of phosphorus over time in those 3-year periods from 1990 to 2019. So we see agricultural soils on the top and then urban soils on the bottom. So we do see that as time goes on from 1990, that the amount of phosphorus that we are applying to our soils and agricultural systems is going down. We can see the amount of phosphorus that we're applying in our urban soils is increasing substantially. So here, the purple color is higher phosphorus and the red color would be lower phosphorus in our soil test values. So I think this is a clear trend, and we do see in our more urbanized counties this greater amounts of phosphorus being applied. This is a trend largely across the entire state. Looking at potassium, we sort of see the opposite. Going forward for potassium, we do see that there's less or lower values of potassium as we go on from 1990 to 2019 for our agricultural soils. And we still see, again, that there's really no change in urban potassium values over this time period. So in my time here at UK in the past 2 years, there's been a lot of changes in the UK pathology lab. And these are the people who've been doing all of this work that I've talked about today. So when I did arrive, Yvonne Schmidt, who was the long-term research analyst in the pathology lab, decided to retire a few months before I arrived. So that gave me the opportunity to hire a new individual for that person, and I hired Rebecca Ramsey. Probably if you're in Ag North, you know her already, but she's been a great addition to the lab. In July of 2019, we also welcomed Dr. Pamela Obura, who's been working on that carbon and phosphorus project along with Drs. Chris Matoka and Hannah Poffenbarger. And then I've also welcomed 2 graduate students to the lab. Annie McGraw, who's doing great work on that sinkhole project, and then Hannah Somerville, who's making great progress on our Fragipan work. I've also had a number of undergraduates who've also come to the lab as well. Haley Anderson, Joey Gordon, and Madison Pride. So with that, there's obviously some names here that I've already said, but just to acknowledge some people who have helped on various projects over the past 2 years, Matt McCauley, Dave Gearing, and the other scientists who've helped us from the Owensboro office, as well as Charlie O'Connell, who got us permission to go to the sites that we sampled our fragipan soils at, and Doctors Lewis Owen and Paula Ferrero, who helped with the dating and teaching us how to actually sample for the dating. I'd also like to thank Jason Bacchus, who helped us with our geochemistry data for our fragipan projects, as well as doctors Chris Matoka, Bradley, and Dave McNear, who provided a lot of guidance for this work. And I just acknowledge my funding source, the Kentucky Cabinet for Health and Family Services. So they continue to provide support, and I thank them for that. So thank you all for your time and attention. That is what I have at this time.
Okay, so let's all give him some clapping. Yeah, there we go. And we'll open it up for questions. So if you have a question, shout out or hold your hand up. Oh, I see you've got something on chat. Oh, Jason is giving you a clap there. Any questions for Chris?
So Chris, this is Ray.
Yeah, hi.
You mentioned a lot of theories with how fragipans develop. Has there been work in trying to make a fragipan in a lab or out in the environment?
You know, I don't know about that. There's been some work around this hydroconsolidation theory and the way that it maybe generates the high bulk densities that we do see. This is actually it's funny that you would ask this. This is actually an idea and conversations that I've actually had with Becca, my lab manager and research analyst, about how we could potentially generate a fragipan in the lab. Just by doing these repeated wet dry cycles over time. I think there are a lot of questions to that, just like the kind of scale of the sampling volume that you would need. Like, would you need to do something like a meter by a meter, or some larger sampling, some larger volume in order to test those ideas? But that is something that we have thought about, and it's something that we would like to move forward with. It's just thinking logistically about what's the most practical way to do that.
Yeah, okay, thank you.
Jason's given you a question on chat that's related to the fragipan. Can you see it there, Chris?
Yes, I do. So Jason asked, if not everybody can see this, with respect to the mineralogy of fragipans, I'm making molecular interpretations from bulk scale data. Do we have plans to look at molecular scale or nanoscale observations of the mineralogy? These observations could provide direct lines for evidence for one theory or another. So yes, we are planning on doing this. Actually, Chris wrote a great section to the proposal to look at SEM scale fragipan coatings, and to then use a laser, which I don't fully understand the mechanics of all of this. We've been working with some people at the UK Microscopy Center to do this, but to then use a laser to actually, I think, get an XRD pattern for the coatings that we do see binding the different particles together. So we can directly quantify those coatings on that scale.
I'll ask a question. When your correlation with sand on the fragipans, have you looked at sort of different size classes of sands? I mean, would you have predictions about fine versus coarse, or any sort of spatial segregation or aggregation there?
So it's likely fine sand, as I would expect. What's closer to the silt size particles are what are driving that relationship. So we are beginning the process of doing the pre-treatments to do the texture segregation in the lab, the separations. So we should be able to separate out all the different sand size fractions for those fragipan horizons.
Looks like Ola has a question for you.
Okay.
Okay. Thank you, Chris. That was a great seminar to hear about what you have been doing. I find your studies on the fragipan pretty interesting, wonderful profile pictures, and Are you interacting with that Fragipan group that has in the meantime found this method of penetrating Fragipan horizons and kind of improving the soil quality? So are you interacting with that group?
So obviously, Chris is on the proposal that we're going to be submitting soon. But I have not myself directly interacted with some of the work that they're doing through the penetration of those fragipans with the annual ryegrass, I believe is the variety. I did go to the field day that they did talk about some of the results that they do have. So what I saw was really interesting and very encouraging. I have, when we did go down to Caldwell County to sample the fragipan there at Princeton, so we actually sampled it on the Princeton farm. Lloyd actually came out with us and we had some really good conversations about the work that they're doing, and then also some of the reasons why maybe they see better penetration and reduction in the fragipan's bulk densities in certain soils versus other soils. And there could be some, reasons why. Maybe the soils that are cemented more with this amorphous lignosilicates, maybe they're more easily broken down by the annual ryegrass than soils that are cemented by these crystalline clay minerals instead.
And I'd like, if that's possible, I'd like to follow up with a few other questions.
Sure.
So with this bulk density relationship, how can you distinguish the typical feature of this relationship for fragipans? Because we know that that relationship is valid for any soil. With increasing sand content, the bulk density increases because sands are the coarsest particles, and they have so to say, the largest mass over the same volume. You cannot create the same mass over the same volume with smaller particles, with silt and clay. Mm-hmm. So how can you say this is typical for fragipans and that it's not just an ordinary finding?
Well, I'm not sure this is typical for fragipans. It's not. I don't know if it is typical for what we've seen. So we have pulled out some data. I pulled out some data from the literature. And I have seen that the relationship between bulk density and sand content doesn't actually exist for fragipans from what I have seen from the literature. So that was one of the reasons why we were kind of encouraged by this result. And I think getting better, as Rebecca suggested with her question about whether or not certain sand fractions are actually driving this bulk density relationship compared to other ones, I think is sort of where answering that question of whether or not this is something particular about fragipans or just something that, okay, this is what we see for all soils. So if it's the fine or very fine sand fraction, that very close to the silt fraction that we know makes up the predominance of these soils, do we see that it is those very fine sands that are driving this bulk density relationship?
Mm-hmm. Okay. Do you have another person trying to ask if that's not the case? So let me know. I can immediately stop if somebody else has a question. Otherwise, I'd like to ask another one on the.
Well, we has put one in on the chat,
Okay,
but
it's
a different project, Ola. So if you want to finish up on that, or
regarding these car systems, so I find it really amazing. This different shape, the horse and the cow sinkholes. So in your schematic of that Catena, is there any, or I learned that both when you open up the profiles, they have different colors. Mm-hmm. One is more brownish and the other one is more reddish. So how do you know up front by being out there in the landscape before opening up a profile? Or is there a way that you can tell up front that this is a horse or this is a cow sinkhole?
I don't know if there is a good way to do that. Some of the way that I have thought about it is getting back to these geomorphological ideas of the flux of particles downslope, diffusion of the soils downslope through soil creep. So as we do get greater and older landscapes and more diffusion over time, we do see sort of like a beveling out of hill slopes. So one of the things that we've done is that we've actually fit this hill slope model, and I don't put much stock into any of this because it is sort of like fitting a model to a particular hill slope sequence shape that we have. But we can fit this model and we can estimate this rate of diffusion over time, and we can get this like diffusion age. So my thinking would just be that if you do see these more gentler looking sinkhole features, they should be somewhat older potentially, and they might have these more redder clay-rich soils in them. And so that is what we did see for these two different sinkholes that we looked at for sales. Whether or not that relationship holds true for all sinkholes, I'm not sure.
Mm-hmm. So did I hear correct that so far you have based your analysis on these two start Catinas, right?
Mm-hmm.
And yeah, okay, this leads too far then, but I'm really later interested in the next year, over the next years, how you approach different sinkholes and what scale relationships you will find out. This is really an interesting topic, and I think it is a very good thing for a pedologist to look into that. So great. So later I have some other questions. So but I would like to first let others know.
Okay. Yeah. No, we can definitely talk more about this off the seminar call too, if you would like.
So Chris, how about Wee's question on
Yeah,
chat?
so we asked any plan to conduct soil carbon and phosphorus coupling study by using modeling and what ecosystems will we work with? The answer is yes. I would love to do that to just sort of get a sense of, turning off certain things, whether or not we do see as a whole that having greater enrichment of the phosphorus does lead to greater carbon sequestration in our soils over longer periods of time, particularly as we move forward into this uncertain sort of climate future. And as for which ecosystems that we would like to look at, we're already looking at managed pasture system, sort of this like annual grass system, but it'd be really interesting, I think, to also expand into forested ecosystems, just because they do make up a large portion of the state as well, and also in the Southeast.
Anyone else have questions out there?
So Hannah asked, do you think the decrease in soil test phosphorus and potassium is due to lower fertilization rates or greater nutrient removal due to crops? So that's an interesting question. I suppose it could be due to both. If you do look at some of the, I think, common ways that we do provide phosphorus fertilizer to crop fields, sometimes they also will include other components to them, like potassium as well. So you can kind of think too that if we're applying less phosphorus, we may end up by accident applying less potassium as well. So that might be one of the other reasons why we are seeing this like down drop in potassium along with phosphorus. But as to whether or not it's due to either lower fertilization rates or greater nutrient removal due to crops, I'm not sure that we can tell from these data that we have.
It might be interesting to look at like fertilizer sales in the different counties and be able to kind of get an estimate of how much fertilizer use has changed over time.
Yeah, that's something that I've actually talked about with Brad some, thinking about like which counties actually have greater or more amounts of a greater cropland. They would obviously have greater influences on the values that we do see within this database. Similarly, counties that have greater urban areas are going to have greater representation than counties that are more rural in spatial distribution as well.
So this is Bob. One thing related to that, and especially I was kind of watching the map in Eastern Kentucky there. Yeah. Over that time frame, we've seen a huge decline in tobacco production and a shift out of that area, which, tobacco soils were sampled annually typically. And so all of that moving out of there, my projection is that we've probably seen those samples disappear they're no longer in the mix. And I think the database actually may have the crop selection might be in the database too. And there might be a way to cross correlate that and see if that's involved or not.
Yeah, so that's also something else that Brad and I have talked about as well, looking at particular crops. Sometimes they even have what they're applying to them, but that's not very common. So yeah, you're correct. Just thinking about what is actually being, what we're applying these nutrients to is definitely something that would be of interest as well.
Do we have a last question? We're almost at 4:10. It looks like Ola has more questions.
Yeah, one question about your statistics class. You started there as 597 and now it is 697.
Correct.
So what makes this class a 697 level class? And the second question, what does the word environmental so characteristic of this class?
So I think the reason why this is a 697 class is that I don't think I could ever imagine an undergraduate taking a graduate level statistics class. And there was a need for more 600 level courses within IPSS. So that was kind of the reasons why I leaned towards doing a 697 instead of the 597, which I think maybe was what Dr. Goff offered the class at originally a few years ago when he was offering that course. To me, the reason why I did this applied environmental statistics was that it was taking environmental data and applying it in R, the analysis of these data in R. And so I wanted to ensure, or I was really trying to think about, okay, if this is a class that anybody could walk in and take, is somebody from, say, Earth and Environmental Sciences, would they be interested in a class coming to IPSS and taking that course and just focusing on, say, experimental research design in plot fields or at the plot scale? So I was trying to get at this sort of we're all doing environmental science, we're just doing it in different ways. And, who can, and I guess providing backgrounds to both people who are doing these plot scale studies and also people who are doing these more observational studies.
Okay, well, great. It's great to see everybody. I'm sure you guys can all see we've got 45 people on here. So thank you all for joining us. It's nice to see all of your faces in one place, and we appreciate your participation. We'll now ask that everyone leave, including Chris, except all the rest of the plant and soil science faculty. So you guys have a great rest of your